Hello everyone, my name is Nomwanga Aisha with my group members Arinda Johnson and Anslin, taking you through our machine learning project, Explainable crowd prediction using density estimations. So looking at the contents of the presentation, we have the introduction, related work, problem statement, research questions and objectives, research contributions, methodology, dataset description, experimental or stimulation results, conclusion, limitations and feature works, references and acknowledgement. So when we look at the introduction, the concept of crowd prediction has become more relevant in recent years due to the rising need for understanding and managing large gatherings of people. Events such as concerts, sports matches, public demonstrations, and urban gatherings pose unique challenges in terms of crowd control, safety and resource allocation. So the traditional methods of crowd management often fall short in providing real-time insights and accurate predictions, leading to the potential inefficiencies and safety risks. For machine learning, particularly deep learning, has emerged as a powerful tool in addressing these challenges by enabling automated analysis of complex visual data and behavioral patterns. So the related work we have here where they worked up deep spatial temporal residue networks for citywide crowd flows predictions. They proposed a deep learning-based approach, which was called the Resonate, to collectively forecast the inflow and outflow of crowds in each and every region of the city. That was the Jumbo Zang. Then also we have the YZN, worked on a multi-size spatial temporal transformer network for short and long-term crowd flow prediction. And looking at the problem statement, so there exists a pressing need to predict crowd presence due to the need to regulate movements and contact between people. The current approaches are ineffective, leading to overcrowding in some places. This emphasizes the importance of developing a machine learning model to address this problem.
Hello, my name is Arinda Johnson, and I'm taking you from here until where I will let my colleague take on and explain the model prediction. So these are our research questions and the objectives. So we wanted to explain how crowd density is achieved, wanted to add interpretability to the different crowd models we used. We wanted to add a contribution to the existing crowd predictions. We wanted to compare the different models. Different models we used the VGG16, a CNN, a vision transformer, and NNM. So the research contributions, we developed a deep learning model for more accurate and real-time object detection. We implemented explainability using Lime and Sharp. As you can see, here, this is the image. And then Lime gets patches where like the yellow lines, they can easily show where crowds are. So this was the methodology we used. So this methodology explains part of our models with more specifically a CNN. So training, an image is fed, then crowd patches are created, and these crowd patches are the ones that are fed into the CNN, create the density maps. And here you can see training scene. After training and evaluating, you fine-tune the data according to the test evaluation results, and you come up with these predictions: low density, high density, medium density. So the data set description, we use the data set that was gotten from GitHub and was normalized to 10 categories, and the images were fine grained and then augmented to increase on the accuracy of our models. On the results of some of our EDA, so we had to create crowd patches for crowd density maps for the various images. And the reason we did this, a density map, it can it blurs out those effects that don't represent the the image, and then brings out the images that stand out. And then these are some of the EDA results.
Hello, my name is Imwagao Aslem, and I'm taking on from here. Yeah, these are one of the extracted features in our data set while we performed our EDA. And as you can see, we had 10 classes, and of which each class had different features. As you can see, these are the outstanding images in each class. For example, immigration, feeling for peace. They each had different images. Now on the next slide, have the results of our models. Our most performing model was a VGG16, matched at 74.63%. And the second best was the CNN. The other models like the ResNet and the Video Transformer, that's the ANN, were overfitting due to various factors that we couldn't do. These are our conclusions. And to our project, learned that crowd prediction based on a lot more factors rather than what we considered as our inputs. For example, we only had images, yet it needs other factors like weather, a lot more factors. Then we face a challenge of limited time upon the training and the building of models to capacity. For example, this is something that we've just got to know about. So most of the things were very new to us, so we couldn't get used to them at the very first stage. But given a new project more time to do better than this. Yeah, the limitations we had were overfitting of our models, which we applied hyperparameter tuning. Hyperparameter tuning in several models, which help to increase the accuracy. For example, the VGG had a 50% accuracy at first, but then later on, after applying hyperparameter tuning, by use Keras tuners, that is also library, for hyperparameter training, it increased its accuracy. Then we had the difficulty in extracting the relevant features from the data. For example, some images were really irrelevant to our cause. And also the real-time inference on resource constrained systems. For example, like we did have access to video footage from cameras, also facial our project that predicts crowds. Yeah. References, this is part of the reference that papers that are related to what we are doing. Yeah, thank you so much for acknowledgements. I'd like to thank Mr. Galiwango Marvin for your help read throughout the semester. We really appreciate Dr. Would also love to thank the computer science department for availing us with a good internet. Thank you so much.